gets made if the other conditions are right, market conditions and pricing and so forth. But from an engineering point of view, you define the problem, figure out how to solve the problem, develop multiple solutions usually, and then you home in on your design. Now, if you break that down further, when you say design the problem or define the problem, what does it mean? How broadly or narrowly do you define the problem? So if I go back to the aerospace industry, if you say, I just want to design something, early airplanes, for example, they were designed more to deliver mail. There used to be mail delivery by stagecoach and, horses and so forth. So they said that takes too long. If I make an airplane fast enough, which can travel maybe 5 times faster in those days compared to the horses, I can deliver the mail. So the problem was defined as, I want to build a machine that will carry mail. Well, it's okay, that can carry some passengers too eventually, but carry the mail so that it will go from place A to B. If that is how you define the problem, you ignore all the sustainability related issues. They say, yeah, I know it creates a pollution. That's okay, but because I can go there faster. And it's only a small amount of pollution, or it's a small amount of whatever. But today, I think knowing what we know, how broadly you define the problem will define what kind of solution you get. And in the context of sustainability, sustainability needs to be included in the problem definition. Of course, there are knowns and unknowns related to the market, the customers, stakeholders. I'm saying stakeholders because the whole world is a stakeholder when it comes to environment and sustainability and so forth. And their priorities may not be the same as your priorities. As a business, as an engineer, you may have certain priorities, but that doesn't have to be the same for other stakeholders. So it's a combination. One needs to understand. Of course, everybody has constraints. They have constraints. We have constraints. We make assumptions, especially for things that we don't know. We make some assumptions. Do we think hard enough, long enough on the impact of the assumptions? If I assume something, it may be very convenient for me now, but do we really understand how things might unfold? How well do we understand the interactions and dependencies? With respect to sustainability, if I make a better airplane, what is the impact on say the environment? If I come up with a better software or better, different way of doing things, what is the dependency? What else does it depend on? What depends on it? Of course, we have to think about resources, and I'm using resources in a very broad sense. People are our fundamental resource. I'll talk about this again later. Knowledge, what do we know? How do we translate that knowledge into some applicable things? Technology, tools, when we talk about digital way of doing things, tools become extremely important. How much money do I have? And more importantly, how much time do I have? Everybody is in a hurry these days. Hey, I'll give you $1 million. What can you do? Well, give me $1 million in 2 years, sir. Well, what if I give you $2 million? Can you do it in 1 year? Sometimes the answer is yes. Many times the answer is not yes, because certain things there is gestation time. It takes time. So time also becomes a very important resource. And today everything is done in a collaborative manner. So it's not just you, it's you plus many other people, suppliers, partners, and so forth. Again, we talked about priorities. How do your priorities match with others' priorities? What constraints do you have? How well do you understand these constraints? And risk. What happens if the approach that you have taken doesn't work out? And this is where it goes back to these interactions and dependencies. The developer of software, I used to develop CFD software many years ago. I understood what to do with it. But if I gave it to someone else, will that someone else be able to run it and generate the same kind of results that I did? Or will they end up doing something where they come to a completely different answer or different kind of conclusion? And then, of course, do we know what the success criteria are? and do our success criteria, are they consistent with those that, the rest of the world? Again, you can pick whichever element of the world, but if you're talking sustainability, it has to be the bigger part of the world. So all these kinds of things one has to think about. These are the drivers for your design process. And again, historically, from the early years, 1900s till about 2000, the process has evolved. Initially, it was just get the damn thing to work. Then we said, hey, I can develop commercial vehicles, military vehicles, all kinds of things I can make, which is what happened in, I would say, about 50 years or so. And then people started realizing, oh my God, these things are getting very expensive. We got to find a way to manage the cost. And that is where we started talking about not just mission performance. We started talking about cost as an independent variable. In fact, there are papers, cost as an independent variable. You can go look it up, and people started saying, we cannot just make something and say this is how much it costs. You have to factor the cost factor. And then later on, people said, cost is not just the cost of making it the first time or making 200 of them the first time. You have to think about how you're going to maintain it over the long haul. So cost now became not just acquisition cost, but the total lifestyle cost. I acquire it, I maintain it, and then I have to dispose it. So I have to factor in everything. And today we are talking about sustainability included. Now, sustainability inclusion doesn't mean all these things go away. You still want to achieve mission performance. You still want to achieve cost goals. Now you also have to think about sustainability and factor that into the mixture. So when you talk about the design performance, we talk about these things. So there are many things that come to my mind. You need to think about the system view of the environmental impact, for example. What kind of a configuration are you going to choose? Because the configuration determines how effective it might be. What materials do you use? There's a huge effort in the industry to replace these toxic metals and high heavy metals with alternatives. Where are your materials coming from? Are they coming from some place? Are these rare materials which are which are destroying the environment in the way you procure the materials? You get these materials out of the earth. Recyclability, of course. Where is your fuel source? People talk a lot about using not petrochemicals, but let's say fuel that is made from plant sources, because they say the plants I can renew. But even then, you are still emitting. Whether I burn fuel that is coming from petroleum sources or from plant sources, I'm still creating emissions. So it has to be thought more holistically. In the manufacturing process, we create damage to the environment. Mining has to do with sourcing of materials, and then of course all these things cannot be ignored. So it gets complex. So can we do it? I think we can. So let's talk about CAE. CAE has come a very long way from say 1970s and 80s. We have aerodynamics, for example. We used to do a huge amount of internal testing. Today, people don't even talk about aerodynamics. Yesterday I was in a meeting, and every time the idea of, hey, is this aerodynamically correct? Immediately the answer was, oh, we'll get a CFD analysis done. So it's almost like people are not thinking aerodynamics anymore. People are thinking CFD, which I think to me is a caution. Aerodynamics is a fundamental physical phenomena. CFD is a model of that physical phenomena. It has definitely helped reduce the number of internal tests that we used to do, but then the physics is getting in our heads. The physics is getting replaced by tools and numbers. Same thing with structural design. Huge amount of benefit from structural analysis tools. Cockpits and control systems have all benefited hugely from the models and digital multifunction displays and so forth. Same is true in the area of propulsion. There used to be a time when it was more of an art than a science. Today, of course, it leverages many of the tools from the digital side, from the computer-aided engineering side. Manufacturing, same way. Today, of course, we also talk about additive manufacturing. Earlier days, we have taken lots and lots of riveted parts, brought them together as a unified structure, integrated structure, and benefited in terms of weight reduction. Testing is going in that direction. Large number of test conditions have been made smaller by using methodologies, not all digital, but using that thought process. And then today, analysis is complementing physical testing. Maintenance also has benefited a lot. We have introduced sensors. We can track all kinds of things. We can do, predictive maintenance even. IVHM is a big thing. It definitely helps in that maintenance area. And when you talk about the design itself, when I joined the industry, it was an iterative process. Long time it used to take, and then you went to this chief engineer, design guru who understood all these interactions between various systems and subsystems. And that individual would guide you and say, let's increase this, let's decrease that, let's try another alternative, let's see what happens. All that got replaced by what we call multidisciplinary design optimization. Today, we are talking about model-based engineering, digital twins, and so forth. But then the question that comes up in my mind is, are these models we are creating, are they factoring in all the key things that have to be factored? And that's the concern that I would have. We have come a long way, but there is a little nagging concern in my head. So the good news, can CAE come to the rescue and help us out in this area? I think the digital tools and methods have become ubiquitous. Everybody uses them now. It wasn't that way, but they have earned their way. They have become more accepted over the decades. And the good news is all these required computing platforms, and those platforms have also become increasingly powerful. Whether it is distributed computing, cloud computing, the computing power available today enables us to do things that we could not do, even 10, 15 years ago. Now, the caution I will leave you with is these tools it is crucial. It is very, very important that these tools are reliable. And when I say tools are reliable, it's not only the tools. Of course, the tool itself has to be reliable, but then it is a combination of the tool and the user. It is also how extensively the tools have been validated, what kind of conditions. Have you simply looked at simple conditions which people understand? Have you looked at complex conditions? Do you have proof that even in complex conditions it works? And then the engineer, because tools alone don't design anything. It's a combination of the people and the tools, along with the process and so forth, that designs things. So it's very important in my mind that engineers do not lose sight of the underlying physics. Use the CFD, use the design tools that you have, but don't forget that CFD is a model for aerodynamics. Certain things can be modeled easily. Certain things are very, very difficult to model. And one needs to always have this in mind, that you should not lose track of the physics. So my observation is that a good engineer can create a good design, outstanding design, even with simple tools. However, if you are a mediocre engineer, you can actually ruin the design even if somebody gave you the most fantastic tool. So while the tools are very important, the engineers are even more important. So those of you, especially younger engineers, don't come and say, I know how to use this tool. That's wonderful. but that's not the sufficient condition. That's a necessary condition these days, that you know how to use a particular tool. The sufficient condition is I not only know how to use the tool, but I understand what this tool is telling me. I know how to look at the data. I know how to extract the kind of information. I know what questions to ask when I'm using the tool, so I can extract that information with the help of the tool. Okay, last chart, sustainability is becoming a requirement in aerospace, definitely. Digital methods and tools offer a way for us to tackle this, but I think I can't re-emphasize the importance of the people in the mixture. They must strengthen their insight. And insight is something that develops over time. So whether you are an individual engineer, whether you are an organization who has engineers within the organization, it's very important to figure out ways to develop that insight, because the tools will help you, but eventually the buck stops with the human being and not with the tool. With that, I will close this presentation. Thank you again for giving me the opportunity to speak. I don't know whether we'll have a chance to, for Q&A. It may not work right now, but I will be around if there are questions to answer. Thank you very much.
Okay. Thank you, Dr. Bala, for your deep insights and holistic perspective in a tell-and-tale manner, driving home the message with absolute clarity. Having listened to the powerful keynote address, we move on to our next keynote address by Dr. Dipankar Chaudhary, Vice President Research on Ansys. So our main sponsor for this program is Ansys. So Ansys is a $1.68 billion simulation company based in Pittsburgh, USA, where SAE International is headquarters is also located. Ansys is working with both SAE International and SAE India for many years to serve our members, and it is one of our their core sectors is aerospace and defense. Dr. Dipankar leads the advanced technological and exploratory R&D in several areas of Ansys Inc., including high performance computing. In addition, he leads Ansys academic program, which includes coordinating collaborating research and educational partnership program with academia oriented engineering simulation. Prior to taking this role, Dr. Dipankar was responsible for Ansys Inc.'s product strategy and planning and corporate product management function. Dr. Dipankar obtained his PhD in the areas of CFD and heat transfer from University of Minnesota. After his graduation, he held engineering and product management position at Crayer Inc. and Fluent Inc., where he was part of the founding group and chief technological officer, and he is a member of ASME and AIAA and has a technical publications in journals, conference proceedings, and trade magazine. Now I request Dr. Dipankar Chaudhary to deliver his special address on advanced solutions to address challenges of next generation aircraft innovation, design, and development. Over to you, Dr. Dipankar.
Thank you very much, Mr. Hassan. How is my audio, by the way?
Yes, sir. You are loud and clear, sir.
Okay, thank you so much. Thanks for that kind introduction, Mr. Hassan. And thank you, Dr. Bharadwaj. You set the stage so beautifully for sustainability and how that fits into the aerospace industry. That gives me a great platform to jump into. I know we are running a little behind in time, so I'll try to be very compact and give you a perspective based on our work with our customers about the place that engineering simulation plays in helping not only better product design, but also sustainable practices. So let me make sure that the slides are advancing fine. Dr. Bharadwaj very eloquently described what sustainability actually means in practice. And the way we can look at it is that really the time is right, because there are the environmental pressures and issues and the social considerations. But in the end, it also makes economic sense and business sense to really look at it in a very organic way as part of the design process. And the way that the new thinking has come into our customers and our partners is to look at sustainability from the lens of how energy is consumed, how it's used, the real-time resource utilization and what happens to the resources, for example, fuel and its emissions, and then look at the very pervasive problem of waste and develop methods and techniques to deal with this waste. With this, I'd like to turn into a view of the
Yeah,
practice.
are you sharing the slides, Dr. Dipankar? Sorry. Are you sharing the slides? We are not able to see your slides if you are sharing it.
Oh, I'm sorry. I'm sharing my screen here.
Okay, we are not able to see the screen. Probably you can reshare it, Dr. Dipankar.
Okay, just 1 second, sorry. Just bear with me. Seeing my screen now?
Yes, it is perfect. Doctor. Yeah,
Yeah,
go ahead.
okay. Apologies. Yeah, thank you for stopping me. So the impact of humans on the environment, I think, has been well quantified, and it manifests itself in all these different considerations. You can from temperature increase to pollution to water issues and global warming, right? But when we look at it from the point of view of what impact it has, and particularly when we ask ourselves a question about commercial aviation, it is a small piece of the pie, but a significant piece of the pie. And that's what we're sort of zooming in today to see what we can do in terms of mitigating that impact. The aviation industry, as Dr. Bharadwaj pointed out, is very keen to deal with sustainability as a root issue right at the design phase. And that's because we are looking at the benefits that have been pointed out in terms of transportation, and that results in more and more use of planes, which in a not so virtuous circle produces more waste, more pollution, more greenhouse gases, and so on. So when we try to drive towards the goals of net zero emissions by improving efficiency, but at the same time keeping our eye on safety and reliability, the challenges become very complex. And the point here is that it's innovations. Dr. Bharadwaj correctly points out that we can make the best tools that we can.
NGS, we did have kind of candidate build is requested by systems team. They do not.
Is somebody getting audio feedback from somebody else? Okay. Anyway, let me continue, Mr. Hassan, and you can mute the other audio. Thanks. And the goal that we have set ourselves as an industry is to improve aircraft efficiency and reduce emissions simultaneously, right? That's quite a steep challenge, but no doubt this is clearly in our minds. There are 6 or 7 ways one can directly impact that, and that's what our customers and partners are working on, all the way from efficient aircraft designs, including weight by lightweighting, high efficiency engines, advanced materials that play into virtually all aspects of an aircraft design, more efficient manufacturing methods, and technologies that result in lower emissions, driving towards zero emissions, and very radical propulsion methods and designs that are somewhat futuristic. So the conceptualization, designing, and developing these futuristic alternatives are something that is a little bit far off, but even today, all the practices that I've described are having an impact. Engineering simulation is a key enabler to achieving these sustainability goals while reducing costs. And there are some ways to look at how this plays out. If we look at the effects of drag reduction, mass, and reducing the impact. And how it boils down to use of engineering simulation is in multiphysics simulations across the spectrum, CFD, thermal structures, electromagnetics, and looking at the performance predictions, looking at reducing environmental impact through reduction of acoustic signatures. And in the arena of time and cost, doing virtual validations, less testing. Of course, that results in less waste, less cost. Simulating as much as we can do within the safe swim lanes of anchored simulation that has been tested, and more innovative manufacturing methods, and even mission planning. So engineering simulation methods have grown from point physics simulations like fluids, structures, thermal, electromagnetics, to a holistic multiphysics view and viewed in the context of a larger system. To the right, you see how the simulation methods can help in selection of fuels, selection of materials, and mitigating emissions through more efficient processes. Okay, I'm going to skip ahead. I think you know about Ansys. We are a premier simulation provider, and the tools and the methods that we have invested in over the years have grown from the discipline areas of structures, fluids, electromagnetics, optical physics, and design methods and photonic simulations to supporting methods that can be looked at from the point of view of optimization, digitization by production of digital twins, safety and embedded software, the very important aspect of materials, not just the data, but the management of the data, and then how it manifests itself into solutions and industries. I want to turn to the last part of my presentation and show some examples of the effective use of engineering simulation methods in different domains within the aircraft industry. One clear successful engineering simulation methods is reducing environmental impact of noise, and through a bunch of tools, not just computational fluid dynamics, but also linking it to noise and vibration analysis and structures, and then translating the simulation data into human audible simulation that can be actually perceived by our ears. So these innovative simulation methods, based on the power of the methods themselves and the platforms that Dr. Bharadwaj also pointed to, has resulted in many benefits throughout the industry. And you can see some of the benefits that have been listed there or quantified, and some quotes here. And to the right, you see some typical applications of engineering simulation to landing gear and other aircraft systems. Another area that is very big in terms of investments, in terms of engineering simulation, is electrification. And of course, the focus here is mostly short to medium haul aircrafts. And the idea is to use a variety of physics-based simulation methods by harnessing CFD, electromagnetics calculations, systems modeling, by putting the detailed simulation, 3D simulation results in the context of an entire system. And the benefits that are being realized are very, very significant. And if in fact these innovative designs can make their way to operating aircraft, the benefits will be very large. On the side of fuels, the idea is to use methods like fuel characterization and selection of blends. These can be simulated nowadays with tools like, for example, Chemkin and Model Fuels Library that characterize more than 60 or 70 different types of fuels. And the end result is that we can combine these simulation methods to produce predictions of how the operational behavior of the fuels would be from an emissions and efficient combustion characteristics. In a very futuristic way, hydrogen combustion modeling is seeing a lot of application of computational methods, CFD and related methods, where we understand and use all these very powerful modeling methods to predict how combustors that utilize hydrogen can actually work in an operating aircraft, including the challenges of the specific volume to energy release of hydrogen. Aircraft drag, of course, is one very direct way in which sustainability characteristics can be improved by reducing the drag, reducing the fuel burn, also increases the economic impact of these higher higher efficiency designs. Material management is a huge part of a design, of course, and engineering simulation methods can enable that with the use of materials information management systems like the Granta design systems, where simply gathering the data and making it available to design engineers makes a more efficient workflow within the design practice and certainly reduces the possibility of wastage, includes the traceability of the materials right from the entire life cycle of the product. So to summarize, we bring it all together into one example where you look at the positive impact of simulation on fuel efficiency. And we have tried to break it down into a number of different rows here, which look at the effects of aerodynamics and lightweighting in the darker brown, the effects on propulsion, and as well as operations in terms of taxiing, flight controls, and very advanced designs with innovative landing gear technologies. And so all the simulation methods really lead and support the innovation in these different realms. One thing I wanted to close with is to point out that, yes, large customers and enterprises are using engineering design methods and tools like ours. And one would think that they are the only ones able to use it, and that's not entirely correct, because a lot of innovation, especially in the arena of sustainability, is happening in small and startup industries. And we have actually increased the footprint of engineering simulation methods by having very attractive programs where we commit to startups and get them started up with these design methods and tools by providing easy access, training, and so on. So we've been very successful in getting small companies going as well in this arena across the world. So the main points I would like to leave you with in my talk is that the goals of improvements in sustainability and the ambitious targets we have set ourselves are really challenging. And it requires really innovative solutions and a transformation of processes and existing methodologies in the industry. These can be very time consuming and indeed sometimes cost prohibitive. But engineering simulation does play an important role by helping this transition process. The buzzword is digitalization, but that's a very key part of what simulation can do for us. And accelerating the pace of progress, I think we'd all agree is a very laudable target. So thank you for giving me the time, and hopefully we can answer questions later. Thanks.
Thank you, Dr. Dipankar, for your focused presentation with the valuable information. Now it's time for our first panel discussion. This panel comprises of eminent aerospace industry leaders across India. In this panel, we are going to discuss about the challenges in achieving sustainable aircraft design objectives, Let me introduce our moderator of the session, Dr. GVV Ravikumar, Associate Vice President, Head Advanced Engineering Services, Infosys. Dr. Ravikumar has led many innovation and applied research projects over the past 25 years. His areas of expertise including mechanical structure, systems, knowledge-based engineering, composites, artificial intelligence, robotics, autonomous systems, AR, VR, and Industry 4.0. He is involved in the development of commercial products like Autolay, Nia Knowledge, and KRTI 4.0. He contributed to many Industry 4.0 implementation projects and played a key role in the development of Industry 4.0 Maturity Index under the umbrella of Acatech, Germany. He is also involved in various initiatives of the World Economic Forum, Fourth Industrial Revolution Technologies in Production. He is the chair for the G31 and member of HM1 Technical Committee of SAE International, contributing to various aerospace standards and developments. Now I request Dr. Ravikumar to take over the panel and moderate the section. Over to you, sir.
Thank you, Hassan. Are you able to hear me?
Yes, sir. You are loud and clear.
Okay. Great. Thank you. Good morning, good afternoon, and good evening, wherever you are across the globe. We have a wonderful panel today. Let me introduce our esteemed panel members. The first panel member, Dr. Kallappa Pattada, is a director of Boeing Research and Technology India. He manages a diverse portfolio of research and technology in aerodynamics, structures, materials, manufacturing, AI, and air traffic management. Dr. Kallappa has over 25 years of experience in the aerospace and defense. Prior to Boeing, he worked at General Motors and Pratt & Whitney, Maruti Suzuki Motors in India. He has about 14 patents in diverse areas. He has a PhD from Pennsylvania State University, US, and bachelor's from IIT Kanpur. Welcome, Dr. Kallappa. The second panel member is Mr. D. Uma Maheshwar. He is a Chief Consulting Engineer, GE Aviation Engineering, India. He and his team are involved in design and development of next generation propulsion systems, support for aircraft fleet, and development of customized digital and engineering software. Uma has more than 29 years of experience in setting up and leading large organizations in engineering R&D. Uma holds an aerospace MBA from Toulouse Business School, France, and ME in mechanical engineering. He has presented many papers. Uma is a member of Global ASME Committee, SAE India Aerospace Board, NAFEMS India Board, and NASCAM Engineering. Welcome, Uma Maheshwar. Third panel member is Mr. Shashi Kumar Muthuswamy. He is an engineering director, aerostructures at Collins Aerospace. He leads highly specialized engineering team that supports design, development, manufacturing, and aftermarket for engine nacelles across most civil airframes, such as wide body, narrow body, and business jets. Shashi has over 21 years of experience in aerospace domain. Okay, he worked with GE Aviation and Rolls-Royce. He has extensive technical and leadership experience in design, development, and certification of large commercial aero engines such as G90, GenX, and Trent XWB. Shashi holds a master's from IIT Madras and executive general management certification from IIM Bangalore. Welcome, Shashi, to this panel. The fourth panel member, Dr. Ganga Reddy, he is aerospace and defense head, HCL. He brings together 20 plus years of rich experience in new product development, testing, project management, and quality assurance. He is spearheading R&D initiatives, design, testing, and validation, process improvement, and systems designing initiatives. He is a member of Aerospace Forum, SAE India. As part of organizing committee, he conducted many conferences, student design competitions in SAE India. Dr. Ganga Reddy holds a PhD in mechanical engineering. Welcome, Dr. Ganga Reddy. The fifth panel member is Dr. Yashan Sridhara. He is Vice Chancellor, Hindustan University. He is postgraduate and PhD degree holder in aerospace engineering from Indian Institute of Science, Bangalore. He served as lecturer, professor, dean, principal, and director of various technical institutes and universities. During his service, Dr. Sridhara developed expertise in pedagogy, research, education, administration, and has contributed immensely to these areas. He connected with industry through consultancy and delivered training programs to engineers and managers of corporates such as GM, GE, Bosch, Tata Motors, and DRDO. Welcome, Dr. Sridhara, to this wonderful panel. So let me give you a kind of quick summary about this particular panel. The topic today, what we are going to discuss is challenges in achieving sustainable aircraft design objectives. So this is the topic that we are going to discuss. If you look at the presentations of Dr. Bala, Dr. Dipankar, they have set the stage very well. Essentially, if you look at it, people, planet, and profit is the broad framework which considers three important factors to achieve sustainability and social responsibility goals. Aerospace industry is backbone of the modern society, which connects the people and moves the goods across the globe. How can aerospace industry maximize its contributions following people, planet, and profit framework? Aerospace industry should have decarbonization strategy and should become the net zero, a carbon industry across its value chain. The industry should have long-standing commitment to reduce environmental impact of its products, services, and manufacturing activities. Understand and minimize the impact on the environment and climate change. Adopt circular business practices to reduce the demand for virgin materials. Safeguard supply and reduce the impacts. Make positive contributions to communities that we operate. Integrity, transparency, honesty, and ethical business practices. Ensure zero harm to all the people and stakeholders and provide best opportunity. The KPIs aerospace industry include reduce energy use in our operations and facilities by 50%, achieve zero greenhouse gas emissions in operations and facilities, reduce total reportable injury rate to 0.3 per 100 employees, reduce total solid and liquid waste in operations and facilities by 25%, achieving zero waste to landfill in operations and facilities. These are some of the important KPIs. According to the International Energy Agency, aviation is likely to be the most difficult transport sector to decarbonize due to the cost and scale of the industry, from airlines to aircraft manufacturers and airports. The aviation industry has made some moves to implement environmentally sustainable practices to fight climate change. A return flight from London to New York City generates over 1 ton of carbon dioxide per passenger. That's nearly the same as what the average citizen in third world country emits in a year. So the aerospace industry needs to improve fuel efficiency, which refers to the distance an aircraft can travel on 1 gallon of fuel. Airbus and Boeing, the two biggest names in the industry, are already producing more efficient planes, such as Airbus A350 XWB and Boeing 787 Dreamliner. Beyond fuel efficient planes, there are other interesting solutions too. Electric aircraft have made inroads in the recent years too. Whether it's hybrid electric aircraft, which means an aircraft propelled by both fuel and electric battery, or fully electric aircraft. However, one of the main challenges facing the electric aircraft is the battery. They remain relatively heavy for aviation. At the same time, jet fuel consists about 14 times more usable energy than a brand new lithium battery. In 2009, International Air Transport Association put in place strategic targets for the aviation industry, including carbon neutral growth from 2020 and reduction in net aviation carbon dioxide emissions of 50% by 2050 relative to 2005 levels. Being carbon neutral is no longer enough, and that a carbon negative economy is the way forward. Combating climate change in the aviation industry is work in progress. One small step in this direction is this SAE India Aerospace Roundtable event. We will discuss challenges in achieving the sustainable aircraft design objectives in this panel. I would like to call upon the first panelist to give his perspective on challenges in achieving the sustainable aircraft design objectives from airframe perspective from Dr. Kalappa. Over to you, Dr. Kalappa.
Thank you, sir, and thanks for having me. My thanks to SAE and Ansys for inviting me, and it's an honor to be part of this distinguished panel. I can assure you, whatever I say, Uma will come after me and take it one step better and so on. So look forward, and I have to just pay my respects to Bala, who had been my manager at Boeing for a long, long time. So I'm following him, and just to follow you and Ravi and the previous speaker. So a few data points. The airspace pre-COVID, 2% of the carbon emission comes from civil aviation. That's the good news. The bad news is it's doubled in about the last 8-9 years. We have about 25,000 aircraft flying, and they're growing at, okay, we will fight COVID and get past it, and the growth will be about 3.5% per year. So in about 20-some years, we'll double that. So on the one hand, you're saying we want to go back to the 2005 emission level. On the other hand, we are doubling our number of airplanes, and these airplanes are much more reliable, much more robust, so they'll be doing many more flights. And there will be a hunger for travel in all the countries, especially the third world countries, as they get better, for the less advantaged people to get on a plane and fly. So that's the first challenge we are all up against. The amount of flying will increase huge. The number of planes will double, and each plane will probably fly double the amount of flights. So you do the math. And in India, we have about, I think, 700 planes, and we count the Indigos, but there are many other airlines, and we're going to get up to about 3,000 by 2040. So that's a big increase. All of these things, I mean, if we fly the way we fly, our emissions will quadruple in India. So that's the number one challenge, is that everybody wants to fly more. Flying is more affordable. In India, per kg per kilometer flight is probably one of the cheapest in the world. So more and more people will fly. And that's the number one challenge. And from an airframe perspective, we break it down into two parts. One is our footprint, the design, the engineering, the manufacturing footprint. And lots has been talked about that, and so I will give a couple of quick examples. Even though we went from metallic aircraft, so one quick thing. 707, which I think was a pioneering aircraft, came out 60 years back, and we had 787, which is another pioneering aircraft that came out about 10 years back. And in that 50-year gap between 07 and 87, the aircraft flying, all put together, not just airframe, engine, everything, air traffic management has become 5 to 10 times more efficient. And we focused on that. Now the focus is on manufacturing also, and I'll give some examples. We went from metal to composite, and a composite manufacturing process is very environmentally intensive. The number of plastic you have to wrap it in before you put it in the autoclave to bake it, that itself is huge. So there are efforts underway to make all of these biodegradable and organic. We apply a lot of paint to the aircraft, and this happens in automotive also. Corrosion inhibitors to the aircraft. That whole application process is extremely environment friendly, and all of these, there is research on to go into organic things there so that it's environment friendly. And that's a big challenge, because at scale, at mass, first coming up with these, producing that, and they actually meet all our safety requirements, is a challenge. In terms of the airframe itself, we've done things like gone to composite, lightweighted it so it becomes more fuel efficient. We've added features like winglets or raked wings, which make it 4 to 5% more efficient. Airspace design has become much more efficient in at least in quite a few countries now. There is flexible airspace concept, there is on-demand route change. That actually increases the efficiency by over 2%. In India, we are trying to build that flexible airspace where defense and commercial airspace can go back and forth. And we did a study for Airport Authority of India. Just designing a good flexible airspace can and having the right equipment on the aircraft can make it 10% more efficient. So the challenge is to make everybody compatible, make the equipment all compatible. You know, we buy some from Raytheon, some from Thales, make all of that compatible and come to that would make it 10% more. Those are the edges that we can trim, really. And that will saturate. It is saturating, and I think Uma will talk about it. And I know Shashi is also an engine background person. They'll talk about how we are saturating in the current designs. Not too much to do. So we do need a paradigm shift. Some change here has to come about. You talked about battery. Batteries are heavy. Their range is limited. If the current design of the aircraft may not be able, take me from Bangalore to Delhi, with the current lift to drag ratios, with the battery storage capacity we may have 10 years from now. So we have to make the aircraft lighter, more aerodynamic, and there has to be some change in the way that is made. Maybe we're going to look at blended wing body aircraft. Boeing is already working with NASA on truss-braced wing, which are huge wings supported by trusses. And then when you have such big wings, you have to modify the airports, you have to modify the runways, you have to change the infrastructure. So it's a holistic thing that needs to be done, sustainability. It cannot be airframe, it cannot be engine. I can go into the challenges with biofuels. If you start doing biofuels, I think those biofuel is the nearest, by the way, because there's too much required to change the aircraft. The logistics are there. Instead of transporting from, in the same tanker, you can transport the aircraft, same way of fueling, but then your crop patterns and everything will change across the globe. That will cause problems. So engine manufacturers, airframe, air traffic controllers, academia, everybody needs to come together to find a holistic solution. If we alone make a truss-braced wing or a blended wing body, which is very good with lift to drag, first of all, blended wing body is something that we did a survey. Passengers don't want to sit in that kind of aircraft. So they feel like they're flying in a fighter jet. So there are lots of stakeholders that Bala talked about. That is a big challenge to get all the stakeholders aligned with a common goal. Airframe obviously is front and center, but others we have all to do this together. The alternatives are in terms of fuel, and people will talk about it, biofuel, electric, hydrogen, all have challenges related to range, all have challenges related to weight. Even if it's 100% battery aircraft, there's no point if it flies from my home to Bangalore airport here in Bangalore. It has to fly from my home to Delhi. The other element that will come into challenge that will come in is urban mobility. We will be having a lot of low altitude, various types of aircraft. If nothing else, even if they are carbon neutral, they will add a lot of noise pollution. So that's another challenge. Right now in urban mobility, we haven't even started having the conversation of environment friendly, and I think this is the time to have that conversation. Otherwise, 20 years from now, we will be where the civil aviation industry is. So these are some challenges and thoughts I wanted to share, and I will wait for questions.
Perfect.
Thank you.
Perfect, Dr. Kallappa. This is wonderful insight. You touched upon multiple things from airframe to engine to the fuel side of it. Now, in the interest of time, we will just move on to the second panelist who comes with a rich engine background. So we would like to hear from him on his perspective on challenges in achieving the sustainable aircraft design objectives from aero engine perspective. Over to you, Dr. Uma.
Yeah. Very good morning to everyone. And I can't think of in the recent times or any time in the history of aviation that I can think of an unprecedented challenge. While we are just in the path of recovery in aviation, now we are talking about completely refreshing the entire aviation technologies. And these are not incremental technologies. Remember, last 70 years or so since the invention of jet engine, we have been actually incrementally improving in terms of fuel reductions, which has been the prime driver. But now we are talking about sustainability, which means the entire focus has to shift from just fuel reduction, which also, by the way, reduces emissions, to dramatically reducing. And what are we talking about? we're talking about making it carbon neutral at some point and actually reducing in the next 15 years, really sustaining the same level of emissions while the whole aviation industry is going to witness growth despite all the pandemic and other, other big disruptions that might happen. It's a significant challenge. And I want to talk about 5 key technologies. What are we doing? And most of this would come from engines because that's where we power the aircraft. And we need to really think of some radically different ideas and technologies. And I'm happy to say that we have been working. The engine makers have been working relentlessly to address the challenge of sustainability. So the first technology I want to talk about is about RISE program, which is about radically innovative architectures for sustainability. Now, we are talking about totally different architectures, and it needs radical innovation. So so these are engines which are about a very high bypass ratio engines. And then we are talking about a huge fan, a culmination of turbo prop and the conventional jet engine technologies. We have launched this program last year in collaboration with our partner Safran, and the goal is to reduce the specific fuel consumption by around 20%. So that's about really taking the current jet engine technologies to next level and also be able to have hybrid electric propulsion and sustainable aviation fuel and whatnot. So that's the first technology where we are investing. And the aircraft will look different, the engines will look different. It is not about just incremental innovation. There are around 300 technologies as part of this program and 15-year program. Second, just in December of last year, we had first commercial flight with United Airways. This is historic flight because it flew 100% on sustainable aviation fuel. We had flights with 50% blend, synthetic and SAF, but this is the first time that we actually demonstrated that we can actually have 100% SAF. And it looks like, what is so big deal because it's just the fuel which is changed, but we need to really understand the long-term implications of using sustainable aviation fuel in terms of reliability, in terms of what it does to the engine. But that's one key technology we see can address the sustainability. The third big announcement that we made was with Boeing, our partners, on powering the commercial. We are talking about large commercial flight with hybrid electric propulsion. And there has been around 200 companies in last 10 plus years working on different types of hybrid electric propulsion, particularly focused on smaller aircraft. But now we are talking about a large commercial aircraft. And I think that will set the path for electrification in aviation. And again, I will talk about the technical challenges if we get time, but this is again a radically different idea. Then the fourth one is very recently we announced partnership with Airbus on hydrogen propulsion. Think about, an aircraft is going to have power through burning hydrogen, and the net emissions would be just water vapor. So 100% you can say sustainable solution, but the kind of technical challenges that we would have are phenomenal because hydrogen needs around 4 times more the capacity in terms of storing fuel as compared to the conventional jet fuel. And we are talking about entire cryogenic system. The hydrogen will be stored as liquid, it will be injected as gas, and then when you burn hydrogen, the flame will be very high speed, almost 10 times to the conventional flame. And then how do you hold the flame? How do you have safety, reliability? And then hydrogen has produces very high temperatures. So all these are the technical challenges, but the good news is we have announced a program, and that's going to again revolutionize the usage of hydrogen. And there is another version of hydrogen, fuel cells, which is also a good solution, which we are also pursuing. And the fifth one is, a technology program which we have been working from last 15 plus years is predominantly coming from military aviation, which is around advanced Brayton cycle. Basically, we are going again is a very fundamental principle of gas turbine, which is on Brayton cycle, and we are going to modify so that we have optimized fuel consumption while in line with the thrust and the power that we need. And we are going to leverage some of these technologies. Now, what does it mean? Each of this looks like a normal thing which we have been hearing, but when you want to really take these concepts into a jet engine, into aviation industry, and industrialize in the next 15 years, we are talking about monumental technological challenges. It's unprecedented. We have used hydrogen in the gas turbines. Our own GE gas turbine business has been using hydrogen as a fuel. But remember, these are stationary gas turbines. Now, the real challenge, I want to end with this. What's the real challenge? There are many challenges: economical, political, societal. There are other things which I will talk about later. Technologically, each of these means addressing some real concerns, particularly from the point of safety. See, today the aviation industry is prospering because it is taken for granted that safety is given. It is the most safest mode of transport. Now, when we are working on these revolutionary technologies, can we develop these technologies to the level that the passengers are used to in terms of safety? That's one. And we don't know how to be certified, right? Nobody knows how to be certified these kind of radically different technologies. So we have to not only address the certification, but make it more reliable to the extent of the current standard. Second, most important, cost. Aviation industry is growing because it's competing with other modes of transport today. Take example of SAF, which doesn't have really many technical challenges other than producing the fuel from alternate sources. You can use existing airports, same infrastructure, just the fuel source is different, but it costs 3 times. Who is going to pay for 3 times more cost, right? So we have to really address these challenges in an economical way, and from technological and design aspects, there are many challenges. So I just want to leave this message that we have invented the future of flight in last 100 plus years, but we are going to reinvent the future of flight for probably the next century, in the next 10 years. So the best times are ahead. It might sound a little ironic that while we are just trying to come out of the pandemic, we are actually going to talk about phenomenal challenges and also phenomenal opportunities. Thank you.
Perfect, Omar. Thank you for articulating those 5 things that you are working and also the challenges involved in each one of them, more specifically using some of these advanced technologies and certification safety you need to ensure. Thank you for that. Wonderful insight. Now, we have covered airframe side, engine side. Now, the next biggest thing is the systems. So I would call upon Shashi to give his perspective on the system side of it. Over to you, Shashi.
Yeah. Okay. Thank you, Dr. Ravi, and good morning, everyone. And it's my pleasure to be part of this SAE conference, and thank you, SAE, as well as Ansys, for giving me this opportunity. I think when it comes to sustainability, right, or emission, everyone.
Ceci, we are not able to hear you. Okay. Come again.
Is it okay? Is it better now?
It's perfect. It's perfect. Yeah.
Okay. Great. Yeah. Sure. So when it comes to sustainability and then fuel emissions, and definitely anyone will go on picking the engine. And I think Uma has very well articulated about the challenges in an engine, and also what are the key things which GE Aviation as such is pioneering in this field. And then Dr. Kalapa talked about the overall airframe side of things. What are the revolutionary airframe structures being pioneered, and what kind of challenges we'll have from an volume growth versus the emission reduction targets. And I would say this is like an ecosystem challenge, what we have now, right? And there are technologies existing and there are new technologies which need to be really created. We always work on the edge of technology in aerospace. And this is an ecosystem challenge for all of us. And Uma talked about the sustainable aviation fuel, right? And in last few years, all the engine makers have certified the SAF, right? And most of the modern engines are certified to fly with sustainable aviation fuel. But the interesting challenge is all about how do we really bring in the best benefit out of SAF, right? SAF has been sort of proven to be providing about 80% CO2 emission reduction through the fuel life cycle. It is not the flight cycle, it is a fuel life cycle. It means where the fuel is produced all the way to transported and delivered to an engine and it burns, then that fuel life cycle has to be designed and technology has to evolve to really gain the benefit of that 80% emission reduction. That's a massive challenge, what we all foresee. At the same time, I see that aerospace industry has always seen many challenges over the years. And COVID was at least in my lifetime, I've seen the tremendous challenges for aerospace, and it has recovered really well, and it's shown a strong resilience. And the leaders who are leading these big corporations are a lot more aspirational. They're fully committed to this climate challenge. And just to quote one of these things, the major event which has happened last year is this Air Transport Action Group. There was a declaration by many of the bigger companies, including Boeing, GE Aviation, Collins Aerospace, including that we will fly net zero carbon emission by 2050, right? So it's a major, bold goal, I would say. And there are big events. If I kind of really put all those, whatever Uma and Kalapa talked about, into a timeline perspective, we are looking at getting the most flights flew by say SAF, and by say mid of this decade, by 2025. And also some of the technologies like hydrogen and electric flights as an alternate source of energy for aircraft, all those technologies have to be demonstrated that it is a viable technology somewhere in, again, mid of this decade. Then we're talking about another like 5 years, and tremendous challenge in terms of developing these technologies, proving and developing the infrastructure. Then from there, we need to kind of go on, say, next decade to look at how we make the hydrogen or electric flights reality, right? Whether it is through a short haul flights, urban air mobility, can we bring the hydrogen as well as electric into a viable product, viable business model? It is affordable for airliners, affordable for passengers. If this is coming in, say, 2035, then all these things will lead to completely decarbonizing aerospace by 2050. Right, so this is a huge technological challenge, huge infrastructure, social challenge, which like everyone in the ecosystem really need to play a major part. So coming to Collins Aerospace, those who don't know Collins, we are the world leader for advanced systems and technology solutions, which we provide for aviation industry and also the space, including civil, business jet, and defense aerospace segments. And we are looking at 2 areas to address the sustainability challenges in front of us. And one is looking at how we can efficiently use the power which is coming from an engine into our systems so that we can drive the fuel efficiency up. And also, how do we complement the efforts of the airframers as well as engine makers in terms of pursuing the alternate sources of power. On the first side, which is talking about how do we drive the efficiency, we are looking at advanced structural solutions for improving the flight efficiency. That includes the aircraft interior as well as exterior structures. We are exploring thermoplastics as a latest advanced composite structures. Thermoplastics proven to be very, very promising material for us to kind of go after, after composites. And we are looking at a significant weight reduction coming out of thermoplastic materials, but it does require a sophisticated, high precision and fully automated manufacturing process line, which we are investing to develop. And that will kind of completely bring in an out of autoclave solutions for thermoplastic as a component. We are looking at replacing some of the major structures like engine nacelles, landing systems, and some of the interior things like the seating systems to interior aircraft structures. looking at bringing in the advanced composites to support. Then we're also looking at the integrated systems to reduce the overall complexity of the systems and also improve the overall performance of the system. It means it rely less on the energy sources. You're looking at the integrated aircraft doors, integrated power, air, and the thermal management for the entire aircraft. There are a lot of research activities going on within Collins. And the other important thing we are looking at is on the ecosystem efficiency. And Collins does support the aircraft, as well as, we have a lot of technology and system solutions for the ground infrastructure, including airport and air traffic management. And we are looking at leveraging the digital and also the wireless technology to bring in the huge amount of data which is required for the pilot to make a decision on optimum routing of the flight. It means you're less in the air, it reduces the overall fuel burn. And so digital technology as such has so much power to bring in all those data together and provide the proper and dynamic data for the pilot to make the appropriate decision. And also looking at collaborating with the airport as well as air traffic management system to simplify and then improve the overall efficiency in terms of decision making. So that will also have a huge benefit in terms of reducing the overall emission reduction from the aircraft. On the second side, in terms of exploring the alternate sources of power, we are collaborating with some of the hybrid propulsion demonstrators with Pratt & Whitney in Canada, as well as working with Airlander in UK to provide a highly efficient and high power motors and as well as propellers to support some of the fully electric aspirations of Airlander hybrid airship. So these are the two broader areas, trying to drive up the efficiency of an existing system so that you can use the power coming from an engine more effectively. And then how do we complement the effort from airframers as well as engine makers on exploring alternate power sources. Right, so with that, I'll conclude my speech and wait for the question and answer sessions. And thank you, Dr. Ravikumar. Thanks, SAE and Ansys once again.
Perfect, Shashi. It is a very well articulation of the various systems, what you are doing from a Collins side to reduce the weight and also improve the sustainability. Beautiful. So the other important dimension, we in India, we do a lot of ER&D services. Now we want to hear from Dr. Ganga Reddy on how these ER&D services are equipped and listen from his perspective on the sustainability aspect. Over to you, Dr. Ganga Reddy.
Thanks, Dr. Ravi. I think you have made my life easy, right? I've heard from airframers and engines and then the systems. We work with all of them, including the academics as well. Professor Sridhara will be waiting because we draw the pool of engineers from the academics who are trained, right? Now, the topic is the challenges in the sustainable aircraft design. That is the objective, right? So whenever I keep meeting the CTOs of many of the tier ones rather than the OEMs, right? So I keep hearing decarbonizing the main thing, right? What does it bring? Everybody has spoken fuel efficiency. For me, this has brought in increased demand for the selective technologies, right? So one is the airframe, the other one is engine. Both Kalapa and then Shroma should not beat me up for bringing in because they are the subject matter expert. For me, in the airframe, it is an incremental, whatever the technologies is demanding, incremental for airframes, probably in weight reduction and then the drag reduction. These are the two things major. The second thing is in terms of engines, right? Revolutionary for engines, I would say. Incremental for airframes, whereas revolutionary for engines. And efficiency improvement. I know GEs and then Rolls-Royce, they are working on ultra high bypass ratio and then open rotor systems. And then how we can contribute there. I know they are the gurus. We can only complement them in terms of with the knowledge from the adjacent industries and also the tools and then the automations which we have developed from the adjacent domains. That is where we can help them in terms of capacity rather than the technology. So to speed up whole of this process. But definitely in the incremental changes or technologies in terms of airframes, we can contribute a lot, because most of the lighter materials, they are adopted from the other industries, which I'll touch upon. And also, Shashi rightly pointed about sustainable aviation fuel, right? And then, so mostly we talk about bio and then municipal waste, or else potentially green hydrogen, or else captured carbon. These are the, SAF. What we are looking at, 10% of this blend SAF in next 1 decade. If somebody says that 50%, 60%, it is not viable. A 10% of SAF blend over the next decade. But the challenges are the scale and cost by 2040, because we have by 2050, we will have to reach a goal of sustainability, right? As of now, 12% of the emissions in the transportations are coming from general aviation or overall aviation. Of course, Kalapa said that is 2% for general aviation, right? That means that how do we contribute? To implement all these things, scale and then the cost is key issue, because by and large your aircrafts are not going to change, right? And your airports are not going to change. So if at all to implement this, you'll have to make some changes into the aircraft, or else the building infrastructure management of the airports as such to accommodate these the sustainable aviation fuels. So the third one is everybody are talking about hydrogen and electric. Of course, we are working with some of the startups in terms of urban air mobility, which will be a reality by 2026 and then or else by 2028 max, right? Provided they get certification. The major challenge is, airframe, everything looks safe, but the power draw, the batteries, everybody spoke, it will be very bulky, and then how do you reduce weight? What we contribute is how can we optimize the weight? We cannot work on the lithium technologies, right? We can. And then what we contribute is, in case of crash landing, how does it behave? How does it affect the whole aircraft? Because that crash simulation, those things, explicit, all those things which we have done it in the other industry domains, that will bring it, and then we try to simulate. We work through the OEMs and then the regulatory bodies as well. Because here regulatory bodies become important. Earlier, over a century, Uma was telling that last 100 years they have developed the aircraft as such. But now the regulations are changing. We'll have to talk to Umas of the world, or else Kalapas of the world, or else Sasis of the world, and then also speak to the regulatory bodies to understand what is the implication. I may simulate, I may design, I give it to you. Whether it is acceptable to the OEMs, the tier ones, or else system integration players, and also the DGCAs, or else FAS. That is where we come in of our experience, right? And then
Perfect.
there are four, probably I know already Professor Sridhara said, don't consume my time. I'll take 1 minute, right? And then I'll wind up. So from the service industry or engineering technology providers, we have been working with many OEMs and then tier ones for more than 2 decades now. We have learned that. And also to augment that knowledge, we have taken the learnings from the adjacent domains like off-highway equipment, or else automotives, or else energy sector. In rotatives, whatever we have learned in the energies, that we'll implement here to by and large, right? During this time, what we foresee is what we can contribute towards the lightweight materials. Like everybody were using thermosets in the era, and now it will be replaced by thermoplastics. For various reasons, it has a competitive edge, it has a processing superiority compared to the one, and also recyclability, which augurs well for the sustainability. I hope all the panel members will agree. So with the moment it becomes lighter energy, uses less energy, which makes them environment friendly as well. Which will go on, right? New propulsion technologies, which I don't want to talk, only about electrification and then battery density. That is where we can pitch in and then we can contribute. And also safe operating conditions, evaluation of safe operating conditions, whether for thermal or structural, or else whenever it crashes, right? In case of dropping, that is where we can help them. And then in terms of
perfect, Dr. Gangareddy, I think in the interest of time, you have very well articulated on the engineering services providers perspective, working with all the OEMs whether it is in the airframe side or engine side or in the system side. Now, let us move on. I think Dr. Sridhara is waiting. One of the most important thing that we have is the skill and competency development, more specifically the next generation people who are going to design the sustainable aircrafts of tomorrow. So we would like to hear from Dr. Sridhara his perspective on the skill and competency development. Over to you, Dr. Sridhara.
Thank you very much, sir. Thanks to Ravi Kumar sir and SAE and all the co-panel members. I think it has been very clearly, being rehearsed, and several times it has been brought onto the stage regarding sustainable developments as aircraft design and maintenance and serviceability is concerned. And it is rightly identified by this particular panel also that the skill development is a very, very important thing. And Ravi Kumar sir, actually, you mentioned very clearly the 3 points on which we can expand, like people, planet, and profit. And if I take the clue from there, and I would like to expand in my first leg here, what exactly are the challenges in terms of the skill development arena that is to be done for sustainable aircraft design, maintenance, and serviceability. The first part which you mentioned is about people. Of course, there is a big challenge to create the human resource who is highly knowledgeable and skilled in relevant field of aircraft design, maintenance, and serviceability, keeping in mind the sustainability and also making it ecology friendly. When I consider the second point which you mentioned about planet, all our activities related to the aircraft shall be ecological friendly, as all of us are actually been telling several times. And the awareness of ecological considerations in all aspects, such as material, processing, reusing, recycling, is the call of the day. If any one of these are actually delinked, I think we are going to have unsustainable development, and therefore all the activities of design, maintenance, and serviceability will be lost. Much has been already practiced in the aircraft industries, and of course, all the aircraft industries are also actually in the process of improving it a little further. And I find that this planet, as given by Ravi sir, is actually to be considered in a very important thing. And of course, I think all of us also know, like any other industry, we also have the decommissioning is a bigger challenge. See, for example, aircraft decommissioning is a greater challenge, mainly because once actually it is declared airworthiness is lost, maybe just because of the time, though it is actually having some sort of, as per the guidelines or as per the requirement of DGCA, it is flyable. But I think as far as the time concerned is concerned, immediately it will be decommissioned. And in such cases, it is really a great challenge because we get huge number of aircrafts to be decommissioned. And this decommissioning, like any ship decommissioning, also is ecological friendly processes is very important. And therefore, ecological friendly processes are the calls of the day. And I have seen actually several pictures, like, maybe about 100 acres to 200 acres or 300 acres of land in a small nations have been actually left out only to just park the decommissioned vehicles and not knowing exactly how do we actually do the decommissioning in an ecological friendly manner. The aircraft decommissioning process comprises the retirement of an aging aircraft from an operational service, storage of potential aircraft reuse, disassembly and disassembling of the aircraft, and recycling of aircraft materials and parts in the secondary market. Again, here the skill development is a major challenge. I think we should consider only one important point, that this being the aircraft design, maintenance, and serviceability is a highly niche area, and a very few institutions, especially at graduate level, are available in India, especially who will be involved in knowledge transfer and also the skill development. We have a greater challenge in, of course, the available workforce or the human force in inculcating these types of ecological considerations into it. So the second point of planet is connected to the people. And now let me come to the third point. The third point, which is mentioned by Ravi Kumar sir, is basically the profit. Of course, when we say ecological consideration, many of the ecological considerations are not properly followed, mainly because they are not economical in terms of direct money or direct the transfer of money or the income. So therefore, most of the ecological practices, when we consider that they are expensive economically, then these are subjected to be negligent or neglected. Therefore, economical considerations play a very major role in defining the process. Thus, a creation of human resource of scientists who are sensitized with ecological and economical consideration is a critical point. So when you take the structural design, manufacturing, testing, operating, and grounding methodology, as our keynote speaker mentioned about all these points, if I take structural design, again, people will look at, I mean, in this particular panel also, people are discussing about having more of simulation than going for, the real test, etc. But when it comes to structural design, although we have several simulation packages, and many of them are highly computerized, etc., and so on. Unless we make a final test in actual working condition, I think we cannot actually come to a conclusion that it is safe or not, something like that. So the structural design part, I think once it is designed commercially using a commercial software or even in-house developed software, it has to be manufactured and tested. So the structural design, then manufacturing and testing, all this actually involve lot of carbon footprints as such, especially the manufacturing and testing, but it is inevitable. How do we reduce these carbon footprints during the manufacturing and testing is a challenge. And of course, when I look at the profit of it, means what should be the economical consideration, and the next part is ecological consideration, as sustainability part is being now looked at. And of course, the whole world is looking for sustainable development goals, SDGs, and then creating a proper skill or the human resource is very, very important. Now, coming to the grounding methodology, which already I mentioned, grounding methodology actually plays a major role. Several times we keep telling that, electrical vehicles at present, if I just take up electrical two-wheeler or four-wheeler to start with, and then come back again to the electric aircrafts, all of us are actually not concentrating. Otherwise, I would say that a few of us are not concentrating on where do we get the electrical energy from. Suppose if I say the electrical energy generation is being taken from fossil fuel resources, maybe coal or even petroleum fuel or whatever it is, then it becomes, I would say, a little foolish to convert this fossil fuel and use this fossil fuel to generate electricity somewhere and pass it through all of them and then come back here and then add it up much more, once more. That is not a considerable one. The moment we make the grid power to come through electrical, non-conventional energy resources, then it is possible to do. So to summarize my talk now, as Ravi Kumar said, the people, planet, and profit, I would say there is a very high requirement of developing highly knowledgeable and skilled in the relevant field of aircraft design, maintenance, and serviceability. Thank you, sir.
Thank you, Dr. Sridhara. That was a wonderful thought. In fact, we are running out of time. We are almost like 10 minutes ahead of the, we have consumed more. What I was thinking is probably we can get some questions from the audience. Anybody has any questions from the audience? And in fact, we have covered all the 5 dimensions, important dimensions, from the OEM side of it, airframe, engines, and the system side. Then we have covered the R&D side of it and also the skill side of it. So it is a very, very comprehensive. So I will just leave the floor open to any questions from anybody. So if there are no questions, I would like to take one question. This is for Dr. Gangareddy. I mean, he has given a lot of insights on the R&D side of it. Most of it, not only the new aircraft, but also the existing aircrafts, right? We need to make sure that the sustenance is ensured, safety is ensured. What best practices that can be adopted to increase the life of structure without compromising the safety and sustainability aspects? Any thoughts from your side, Dr. Gangareddy? You are speaking on mute, Dr. Gangareddy. Yeah.
Sorry, I was on mute. So the broader topic which you have brought in, some of the best practices which we have cross-leveraged from the adjacent domains, I was telling you earlier, the quality process, aerospace quality process was different from the automotive perspective. The Kpis of the world we have brought in now, which is very well acceptable because of our long-standing association with the automotive industry. We have brought in all the 18 phases of PPAP ensures that there is no escapes in terms of quality, because you are reaching sustainability at should not be at the cost of quality, right? So that is what one of the best practices which we have leveraged from the adjacent domain, Dr. In the interest of time, I can go on. We have developed the EDAT, that is electronic test tools, which can be used across multiple domains, right? Or is one test embedded for all your avionic components while testing, which is much more faster. These are some of the tools which we have developed over the years, which we have developed for other domains, but we have brought in here.
Okay. No, that's wonderful, Dr. Gangareddy. I think we can have one more question. Anybody from audience?
Dr. Ravi, there are some questions in the chat.
Some questions, Ravi.
Oh, okay. I think that's good. Yeah, there is one question that was there in the early. Oh, okay. Yeah, excellent, excellent. There is one question that I would like to pick it up. This is coming from Rajamani.
Hello, sir. Good afternoon, everyone.
Go ahead, Rajamani. Yeah.
Yeah. So, thank you for the opportunity. I would like to know from the panel members their views on the development of electrical powered aircrafts and their practical application in the improvement of the current aerospace industry. How it is going to replace the existing power plants.
Thank you, Rajamani.
This question.
Yeah, so he's asking about the electrical powered aircrafts and their practical applications for improvement in the aerospace industry.
So I want to basically talk about this on two aspects. One, the quest for using more electric power has been there. 787 aircraft, for example, is one of the finest example of all electric aircraft. So when we look at it from the subsystem standpoint, that journey has started long time ago. And if you see from there on, whether it is Airbus, Boeing, you name it, there has been effort to use more and more electricity in the aircraft, and that way reduce the fuel consumption. But having said that, now we are talking about how do we use hybrid electric propulsion. So either fully electric aircraft or in combination of a small gas turbine. So the forecast is that up to say 19-seater passenger, and maybe a little later up to say 40-50-seater passenger, we would see hybrid electric aircraft. Today, fully electric aircraft are being designed, up to say 4 to 8-seater. So they are commercially available. Particularly they started with pilot training. Now for 2-seater, then 4-seater, then up to 8-seater, fully electric aircraft. Beyond that, it doesn't work out from the economy, from the weight and efficiency standpoint. So you need a small gas turbine. So I foresee that in say 15 years from now, we would have commercial airlines offering tickets with hybrid electric propulsion. It's a real. And I talked about our partnership with Boeing. This is again not on a small aircraft. It is on a decent size aircraft. We would demonstrate, and the good news is that we have already demonstrated with all the systems. With the motor, the batteries, the integration. We just need to put it onto an aircraft and just fly, and then we will learn something, and then ultimately it will go towards certification. So there has been a lot of effort already, and I'm sure for other OEMs as well. So I can say that it is real, and in the current engines, current aircraft, there could be an application of increasing more electrification if we know how to take advantage of the battery technology, but more so in the new aircraft and the new engines.
Perfect, Uma. I think.
Uma, can I?
Yeah, go ahead.
Can I
go ahead.
Add to that? Yeah, or we could go to other questions. It's your call, Ravi.
There is one more question, Ravi, on the hydrogen.
One more question. Probably what we'll do is we will collate all these questions. We can provide them offline as well. So last questions, probably we can just look at it. This is coming from Archana Menon, and she says in our country, aerospace automotive industry is working with the government to support, develop the sustainable power grid for charging EVs. Okay, so it is more of a comment. Yes, they are working on it. But any pointers, any thoughts from Dr. Kallappa? Probably you can take that question.
I'm not an automotive person anymore, so I don't know what's going on there. And in the aerospace industry, like Uma said, we're just testing it at scale now. So those conversations have not come up yet. The focus in aerospace in the nearest future, and I think everybody will agree, is more on SAF, the sustainable aviation fuel. Those tests are going on at scale. The electrification part, as far as I know, are we working with the government to develop a sustainable power grid for civil aviation? I'm not aware of that. Maybe somebody else is.
Right. No, I agree. A lot of effort is there on the land vehicles, but in the aerospace, yeah, it is at two.
So it's a crawl, walk, run thing. I mean, we're still in the crawl phase here.
Right.
Sir, quickly, I just would like to just add one point to it. Basically, the question is whether the government they support the development, support and develop sustainable power grid. Basically, on the sustainable power grid for charging EVs, of course, there are many, plenty of them are actually playing this, including few state governments and central government policies are also coming through. And we can see, especially in the major cities, many, the grids are being generated. I mean, the power which is actually generated by non-conventional energy resources, that is renewable resources, are being plugged in as the charging stations, and this must increase. And if it increases, probably we'll have sustainable development. Thank you, sir.
Right. No, that's a wonderful thought. So probably what we will do is, all of you, in the interest of time, you can send out the questions. We'll collate them, and we will send all those answers offline. And this is a very, very interesting topic. Definitely, it is closer to our heart. As we discussed, people, planet, profit. These are the 3P framework that everybody is working towards, and aerospace industry is doing a lot, and I see a lot of stuff that is coming on as we move along. And thank you, the entire panel members here. It's a wonderful panel discussion. Thank you. Thanks a lot for your time. Over to you, Hassan.
Thank you, sir. Thanks a lot. Dr. Ravi Kumar, for the moderating the experts roundtable and the excellent input from Mr. Uma, Dr. Ganga, Dr. Sridhara, and Dr. Kallappa. Thank you, sir. And with this, we'll have a short break for 5 minutes before our next session will start